This is the proof of the mean value theorem for integrals for Calculus 2. To prove the mean value theorem, we use the intermediate value theorem, and I'll state it here in case you need to recall it. The intermediate value theorem states that if f is continuous, so we start with a continuous function on some interval a, b. And now let's look at the endpoints. So f of a is going to be the function that the value that the function takes on at one endpoint, and f of b is the value the function takes on at another endpoint. Then if n is any value between those two numbers, then there is some value of x within ab such that the function is actually equal to that number. Okay, that's a lot of words. What it basically states that if the function is continuous, then it takes on all values between any two endpoints. You might say that's intuitively obvious, and it is, but we always have to state it here in math. Okay, so here's our example. This is the arc cosine function. Right? When x is minus 1, the arc cosine function is pi. When x is 1, the arc cosine function is 0. So the two endpoints, the values at the two endpoints are pi and 0. The function states, the theorem states that the function takes on every value between pi and 0, between minus 1 and 1. So here's the proof of the mean value theorem. Again, we need the continuity of f. So f is going to be continuous on some interval ab. And let's say a is not equal to b so that we can divide by it without having a problem. And let's let f min and f max be the global max and global min of f on ab. All right, I'll just give you some an example here, what we're talking about. So let's say we have some function and it looks like, whoa, that's a line I want to pin. That looks like, maybe it looks like this. Fine. Okay. So let's say this is the maximum value of it. And here, it doesn't necessarily have to be at the end point, but this is the minimum value of this function, and it's a continuous function. All right. So the function itself, all the values of the function lie between the minimum and the maximum. Now, in terms of integrals, I know that if I take the minimum and multiply by b minus a, that's going to be less than that integral over the whole function, because this is the minimum value. F min times b minus a for this positive function is just the area right under here. All right. Then this definite integral, which in the case that I've shown here would be, put this in red, would be this whole area. Okay, that's going to be less than the max times b minus a, which would just be that squared off area. And obviously that's bigger. Okay, now divide by b minus a, which is why we need to have a not equal to b up here, and I have f min is less than or equal to 1 over b minus a times the integral of a to b f of x, which is less than or equal to f max. Right. Now, by that intermediate value theorem, the function assumes all values between the minimum and the maximum. So if this value lies between the minimum and the maximum, which it does by our construction here, then the function achieves this value. It achieves it at some x in the interval ab. That's what the intermediate value theorem says. So to state that, oops, sorry about that. There's an interaction between the scrolling and the pin function. So what we're saying here is there is some c, some value of x in ab, such that the function evaluated at c would be equal to 1 over b minus a times the integral of a to b of f of x, which is, by definition, the average value of the function. And here again is the graph, so demonstrating that result. So let's say the function is x squared, which is a continuous function, and this will be a, and 2 is the value of b. Now, if I take the average of x squared between 0 and 2, I find that the average value is 4/3, and 4/3 is one of the values that the function achieves on the interval a to b. It achieves it at least once. Okay, and that's all that it says. In other words, the average for this function on AB is not some number way up here that it doesn't even achieve, or some number way down there. And that's the proof. If you're really clever, you could probably write that in one line, 1 or 2 lines.